Okay, so just to start with, I have done a few things here on my paraview visualization to show you what can be done. Okay, so that box up there is a text box where you can put some sort of text together with your picture. Annotate time will give me the count of the time steps. And now when I click on the play button, you can have the discretization for the whole thing from start time till end time. Now in this case, diffusion coefficient is set to 0, which means that my step profile from the inlet should be carried around by the velocity field to the outlet without deformation. So this result is actually quite bad. And what I would like to do now is first find out why the result is so bad. And second, see what we can do to get this result looking better. Okay? There are two reasons. First, I'm using Euler's scheme in time, which is first order accurate, and I'm using Upwind's scheme in convection, which is also first order accurate, meaning that they both carry the discretization error, which is of diffusion type, and that explains why the profile on this side looks so smeared. Okay, so for the first trick, we will try and rerun this with second order discretization in space. Now if I jump to the beginning and go through the time steps, you can see that that solution is not quite right, because my variable that used to be between 0 and 1 is now going up to 1.243, and the whole thing looks quite oscillatory. Okay, on the positive side, you can see that the profile is sharper, but these values that are greater than 1 are really not acceptable. Okay, so to give you an indication, imagine if my variable is concentration, that would mean that I have concentration of 121%, which is unphysical within the model that I'm running. Also down here, I have the negative values of minus 0.2. Okay, so you can see that it's got wrinkles on both sides of the step. So what I can do here is use a second order bounded scheme, like for example Van Leer, and rerun the simulation, going back to the beginning. The profile now stays bounded, okay, and the whole thing looks a bit prettier, and it remains between 0 and 1, which is the most important thing. However, if you take a look at temporal variation, this here should also be a step profile, right? And you can see that it is quite smeared. Okay? So what I can do to fix that is to change the temporal discretization scheme into something called bounded backward, which will now give me an even better profile in time, but not significantly better in space. Okay, what is the message? The message is that the discretization methods, even those which are strictly bounded, are really not great. Okay, so take a look at what approximation I have of the profile. Does anyone know how I can fix this?
From the mesh.
More mesh, exactly. So that is the only solution that I have for you. Please have in mind that this level of discretization error is considered normal, okay? And that it is not what I would get with upwind differencing, but it is still much better than what I started with, okay? So getting perfect analytical solutions will require quite a lot of care, quite a lot of mesh, etc. Okay? What is the other thing that I can improve this? Drop the time step. Okay, that will sort out the temporal part of numerical diffusion error, but not of the spatial part as well. Okay? If you would like to have a play, please do so now. We are getting close to 5 o'clock, so I think that will be enough for today. In order for me to prepare for tomorrow, we need to discuss the presentations and the examples that you would like to do. Okay? Can I have some ideas from the audience, please? Okay, so we can do meshing with snappy. You want to do that?
Turbulence.
Okay.
Turbulence.
Turbulence. What precisely about turbulence?
LES.
Okay, well, LES is like this, so I think we'll give you homework to run one of the LES examples. Okay, I will go through the discretization settings for larger dissimulation, which is the important part of the story. Okay, the third one, definitely discretization best practice. I need to show you how to set up the code.
Maybe something with multi-phase?
And multi-phase. Okay, so those are the 4 examples. On the multi-phase example, tomorrow we will do the dam break, and I will show you how to run in parallel. But again, I think we should keep ourselves to 10, 20, 50, 100,000 cells rather than running something really big, right? Okay. Usually, at the end of these stories, I have about an hour and a half, maybe an hour, to discuss problems from the audience. Okay? Do we still want to do that? Okay. If you have any meshes or cases or anything like that that we need to take a look at and you're allowed to show it in front of the audience, please bring them with you and show me tomorrow morning. Okay? We have slot for one more presentation. And let me show you what I've got on the list. User view we've done, NACA Wing tutorial we've done, scalar transport walkthrough we've done. I have promised discretization best practice, multi-phase, and snappy. Okay? We have the Ahmed body tutorial, which comes with snappy, dynamic mesh, or C++ introduction. Okay? How many of you need to do coding in OpenFOAM? You know C++ properly? Okay. There is another one that I do, which is called 5 basic classes, okay, which will help you understanding the details, but we've done parts of that on the scalar transport. Okay, so shall we just leave it at that and review at lunchtime tomorrow? Okay, so tomorrow morning we will start with multi-phase, then running in parallel, then discretization best practice, and then snappy. Okay? Good. I think that's enough for today. See you tomorrow at 9 o'clock.